Hey everyone, welcome back. So today we are going to have the final lecture. All right, guys. Let's probably wait for another 10 seconds in case if anyone has any question. Feel free to just ping your question in the chat. We'll be wrapping up with deep learning and chatbots in today's lecture, and post that you will be completing your NLP lectures. So if you have any particular question, you can let me know. Okay, I guess there are no questions. Let's begin. Let me share my screen. So in today's lecture, we'll look at deep learning side in NLP, and we'll talk about chatbots. Okay, so starting with the first topic, I think you all know what is deep learning, so I won't cover the basics of deep learning. Um, Coming to how do we utilize deep learning in NLP? So traditional ML models may not give you the best results, considering they are not able to handle vast amount of data and the complexity which comes with the text data. It's something which may be very difficult to handle by the classical ML models. And that is where you can use deep learning models to get better results, considering you don't care about feature importance. Okay. So you can use it for multiple applications. And even today, some of the real world applications are based on deep learning itself. Okay. Right. So advantage of deep learning, can learn relationship between words and phrases in a sentence, in a language. So this is a very powerful thing because now you're able to understand the context. You're able to understand the meaning through deep learning. Okay, and I think we have seen about word to vec, which is again based on deep learning itself. Okay. So talking about which DL models we are going to talk about. So one is RNN, right? So RNN, we know it can process sequential data. Okay, you might have seen this in time series forecasting or any other previous model. Then we are going to talk about transformers. We don't need to go into the architecture of transformers because it's highly complex. It's not needed for now. But transformers is working on the logic of attention. So it's basically self-attention. Okay. Self-attention, and this captures relationship between the words. Okay, so it tries to understand the overall pattern between the words, and that's what will happen through transform. So it's kind of understanding context only. Okay. So transformers are the one which give you the output of chat GPT, GPT-3 or GPT-4. Okay. So these are the ones which are highly powerful. And obviously they are highly complex and not so easy to build as. Right? What else? Then we have CNN, which is convolutional neural networks, right? So convolutional neural networks you would have seen in image processing. This can also be used in text classification. And let's say sentiment analysis. Okay, I think you all know the architecture of CNN, where we have convolutional layers, right? Right. So we have basically convolutional layers which apply filters to create the features, to extract the features of the input. Right. And then after that, you have convolution layers, you have pooling layers. Okay. So you apply pooling. Okay, for downsampling your output. Okay, and finally you have like fully connected layers. In short, like this can change, but in short, generally this is how the architecture looks like. Okay. One more thing, when we talk about RN, one model which comes along with RN is your LSTM. Okay. So again, you have seen this long short term memory network. Okay. The main concept is based on gates, okay, which control the flow of what information to pass based on the hidden state. Okay. So this is highly useful for retaining long-term information. Okay. And that is why we can use it for, let's say, if you want to translate words, so language translation or machine translation, which basically means like if you want to translate language from one language to the other. Okay. So I think all the other architectures we have seen, one architecture which probably we have not seen until now is transformers. Okay. So transformers is very like recent. It's not a old architecture. So it's a recent algorithm with very high performance. So as I said, they use a concept of self-attention. Do you guys know what is self-attention? Can anyone confirm in the chat if you know what is the meaning of self-attention? Have you studied self-attention in deep learning? Have you guys studied self-attention? So I guess it's a no. So you haven't seen self-attention. Okay. So let's discuss about self-attention. What is the concept? So self-attention simply implies that okay. So as the name says, right, self-attention. What will happen over here is the algorithm which uses self-attention, it will look at the sentence. Okay, it will look at the sentence and it will understand what is the context it's looking for. Okay, context it needs. It will try to understand by looking at the sentence. How does that happen? It happens by it assigns a query to every word in the sentence. Okay, so let's say there is a sentence. He is playing golf. To every single word, you will attach a query. Okay, I'll explain what is query. This query, whatever we are getting attached over here, we will be comparing this with keys. Okay. Okay. So over here, you will combine it with key and key will have corresponding values. Okay. So what happens is query implies a matrix which is focused on focus words. Okay. Focus words as in the words which will determine the context. Okay. So what happens is you will be creating a matrix where you will be transforming, the word representation using the query matrix. So you'll be like generating a query vector, which will be combined to create a matrix. Okay. So over here, you will be simply query vector means like you'll be transforming it into numbers. Okay. So you would be only transforming those words which you feel are important. Okay. So over here, let's say if you have the word wolf and let's say play, you will get a query vector for this. You will get a query vector for this. Okay. And now I can simply store it as a matrix form where you have a matrix of the important ones. Okay. This Q1 and Q2 will be a numerical value like 1, 0, 7, 8, and so on. Over here, I can simply compare Q1 and Q2 to understand how similar both the words are. Okay, and notice they are only the important words which will help you understand the context. Okay, second part is key. So key is again a matrix which is used to create key vectors. It's a matrix of key vectors. So what are these key vectors? Key vectors are basically vectors which contain similarity between the query vectors. Okay, so once you have converted your words into vectors like Q1 and Q2, the similarity between Q1 and Q2 will be stored in key vectors. Okay, so it will contain the similarity between all the focus words that you have. Okay, and based on that, it will create a matrix. What will happen over here? The higher key score or a higher value in the key matrix represents a higher similarity score. So basically, if you see a high value in the key matrix, it implies that both the query vectors, both the words, focus words, were very similar to each other. Okay, so it talks about, in short, key matrix is going to talk about how strong the relationship is between focus word. How strong is the relationship between focus words? Okay, next you have value. Okay, so the last one, value. Again, this is a matrix. Okay, so this will generate value vectors for every word in the sentence. So we have generated key vectors, we have generated query vectors. Now we are generating value vectors. Okay, so what will happen? These vectors will hold the contextual information of each word. So once we have calculated the similarity scores using the query and key logic, the system, the algorithm will compute a weighted sum of the value vectors. Okay, so this will compute a weighted sum of the value vectors. Okay, where the weights are going to be determined for every single vector by the similarity scores. Okay. So what will happen is you will compute the key vector, right? In key vector, you will get your similarity score for everyone. Like there is Q1, there is Q2, there is Q3, there is Q4, there is Q5. For each one of them, you will get what is the similarity between each one of them. Let's say between Q, like this will be in matrix form. So let me write Q1, Q2, Q3, Q4, Q5, right? What is the similarity between Q1 and Q1? So obviously it will be 100%. So this is, let's say, 1. Q1 and Q2. So let's say this is 0.3. Q1 and Q3, this is 0.7. Q1 and Q4, let's say this is 0.9. Q1 and Q5, this is, let's say, 0.8. And so on, you can fill for the rest as well. Okay, so now what will happen is when you finally try to create the value vector, okay, when we try to create the value vector, I want to generate value vectors by focusing on the words which are highly influencing the context. Okay. So since we have already identified the focus words, all the words are somewhat going to, you know, uh, somewhat going to alter or impact the context. But every word will have some kind of impact. Like maybe Q1, the first word, may impact the word, but the impact will be high. But Q2 will also impact it, but maybe the impact would be medium, right? So based, if I can figure out how much impact that they are going to cause on the final sentence, on the context, if I can figure out that, I will simply take that into account to compute the weights. So I will say if Q1 is impacting a lot, I will assign a high weight. I will assign a high weight to Q1, and Q2 ko, since it has a medium impact, I'll assign a medium weight, and this weight I'll multiply with its similarity score. Okay, wherever I am having Q1 along with a particular, like for whatever relationship I'm trying to look for, I will use that similarity score with the weight attached. Okay, so we'll talk about an example just after this, but the logic is the weights will be created, based will be created based on the influence of the focus words, how much influence they can cause, or the impact caused by focus words. Okay. So in summary, what did we learn? We learned that there are query matrix, there is a key matrix, there's a value matrix. Query is nothing but a vector representation. Key is nothing but a cosine, not cosine. It can be cosine similarity as well, but it helps you to compute similarity between the query vectors. And value is nothing but a weighted sum of all the cosine similarities, all of the similarities, okay, based on the impactful words, so that more important word is given more weightage. Okay, so this together will help you in understanding the context. Okay, and it's a very effective method because through this you will be able to understand the context, the final representation of the focus words. So so any self attention mechanism will have the query, key, and value architecture in them, the three matrices. Okay, this will create deep layered models, okay, which can process your text. Okay, so talking about how does it, like talking about an example. So once you have the text data, you will pass this text data, which will be converted into your embeddings, right? You will have your numerical representation, which is your word embeddings. Okay, once you have the numerical representation of the words, um, next we'll pass it into the attention mechanism, where you will be passing into the transformer, where you will have your QKV, right? Your query, key, value. Okay, so over here there are like multiple types of architecture of transformer as well. Okay, so one of the architecture is where, let's say you want to run. Okay, let me actually show you a diagram. So Okay, just give me a moment. All right. Okay, so continuing from where we left off, I just want to show you one diagram. Okay, so which is, yeah, let's check this diagram. Let me share the screen. So if you look at this diagram, this is the diagram of your attention mechanism, okay, where you are passing your input of n rows and d columns, right? So this is assuming like you are passing it in form of words. Now you are going to compute the weights, which is your first layer, where you compute based on different dimensions what are the weights that are going to get attached. Based on that, you'll be computing your Q, K, and V, which is nothing but your query, key, and value matrices. Query will simply just cut. Okay, so this, let me just show you over here. Okay, so if you see over here, first you're converting everything into numerical form. Okay, it's an embedded sentence. So where you're passing like this word, life is short, eat dessert first, it will compute what is the embedding for every single word. Okay, the numerical representation. Okay. Next, once you have the embeddings, it will compute the query matrix, the key matrix, and the value matrix. Okay. To compute all these things, it needs weights, right? Because it's an attached layer. So it will compute your query matrix, it will compute your key matrix, and it will compute your value matrix for every single word. Okay. For X word, X1, X2, X3, for every single word, you will have query, key, and value. Okay. Now, once that happens, once you have created the weights, these are all unnormalized, not uh, defined by their uh, weights. Have they mentioned about computing the okay. So over here, query is the representation, key is the similarity scores in numerical form, and V is uh, the final cosine the similarity scores based on their importance, okay, based on their weights. Right. So they have not mentioned about QKV, but we know that QKV represents the same thing. They have not given over here. Okay, so once you create this layer of every single word having three matrices, which is Q, K, V, what will happen is finally, in the final step, we need to take a dot product. Okay, this dot product is what we call it as the self dot product. This is the dot product for which you'll have to take a dot product between the query and the key. Okay, the formula is Qt into K, Qt dot K. This is the formula which gives you the final weights. Okay, so we compute Wij based on this formula, which is Qt into Kj. Okay, so basically you are multiplying the vectors with their similarity scores. This will give you, if you see over here, this will give you this final weights which are computed W21, W22, W2T. Okay, these are computed for all the query 2 vectors. See, like you're passing x2. For that, you have a query 2. For query 2, you are multiplying query 2 with all the set of similarity scores. Okay, with respect to the first word, with respect to the second word, with respect to the T word. Okay, but notice you are doing it only for query 2. Okay, so this for query 2, query 2, query 2, you will get W21, W22, W2T, which are all the weights for different like combination of words with the word 2. Once you get all these weights like W21, W22, W2T, all you need to do is finally combine them. To combine them, you can use your fully connected layers. You can use your at the end, finally, you can apply some layer output layer. Okay, you can apply some stacking. You can apply normalization. You can use ReLU. Okay, or if you want to use any other final architecture layer, you can use that, like anything which you want to use for activation or normalization. But so once we have the result from the weighted sum, right? Once we have the dot product done, once we have the dot product um, between the Q and the K matrices. Okay. So over here, we'll finally try to concat all the results. Okay. So here you are having alpha 21, alpha 22, alpha 2t, which is nothing but you're just applying a softmax layer. Okay. So this is just a normalization factor which we have taken based on the number of dimensions, but it's fine. Like normalization is not like a key state. It's just helping you to normalize it. So as you can see, like it's a, you're just dividing it by to scale the particular vector. Okay. Okay. So over here, they are talking about Euclidean length, but we can discuss about cosine similarity as well, which we can do to find out the similarity. Okay. So Euclidean, I don't think so. It's a very good choice for computing distances, especially in this example. We'll talk about something better. Okay. So finally, you apply the softmax layer and you get the final alpha 1, alpha 2, and alpha till alpha t. Okay. So once these alphas are received by applying the softmax layer, you will have your final output, which would basically represent your probabilities, right? Whatever words you have, what are the different probabilities? Like for the first word, what is the probability of that word? Okay. Secondly, for the different word based on the context, like if you're trying to predict, if you're trying to, let's say, translate a word into any other foreign language, so it will give you a probability that what could be the other foreign language word for the same word. For example, what is the foreign word for the word table, right? For English, what is like the Chinese word. So you'll have like options and it will score the probabilities between them. Okay, so we'll take an example of this just to wrap up. So let's say the sentence is the cat sat on the mat. Okay, the cat sat on the mat. So first step, we need to convert the input, the text into the embedding, right? So the cat sat on the mat. Considering we only focus on the focus words, we can remove all the stop words and all the unimportant words. Okay. So let's take one word and start with that. Let's say we are focusing on the word sat. Okay. So now what will we do? For this, we'll compute the query vector, which is the Q matrix. Okay. We'll compute the Q matrix, we'll compute the key matrix, and we'll compute the value matrix. Okay. So once we convert SAT into the word embedding forms, what will happen? Depends on the embedding that you're using, but you will get a numerical representation. We already know how to convert it into embeddings, right? So let's say for SAT, the representation is minus 0.37, 0.72, okay, and let's say 0.45. This is the representation in word embedding form. Okay. Now next, what will happen to compute QKV? Um, You would be computing the Q, KV, but remember to compute all this, you need to calculate the weights as well, right? Because in any neural network architecture, you can't connect multiple dots without having the respective weights. Okay, so we'll see how we can do that. Okay. So to compute the query vector, start with initializing a random weight attached to it, like compute WQ, which keep it any random numbers. Let's say we keep it randomly 0.1, 0.2, 0.3. A random assignment. Good. Next, similarly to compute key vector, we'll compute random assignment of the weights of key vector as well. Let's say minus 0.9, 0.8, minus 0.7. Okay. Similarly for value, we'll compute randomly, which is 0.2, 0.3, 0.4. Okay, I'm just taking random examples. Now, for the word SAT, what will happen? We'll compute the query matrix. Okay, let's call this query matrix as query SAT. How will we get this? We'll get this by initial representation of SAT, right? So let's say initial representation of SAT, what was the embedding? The embedding was minus 0.3, 7.2, and 4.5. Okay, this was the original representation. This will have to multiply it with the weights, right? So we'll multiply this with the weight, whatever was the random weight, and you'll get the final matrix. Okay. So let's say you have WQ over here. You can multiply WQ to get your first number. Okay. So over here, what will be right is, okay, this is your first iteration. Okay, this is your random vector, random weight. Okay, let's say you'll get some number. Let's say 0.5, 0.4, 0.8. Similarly, you will do it for K sat as well. You will take the same embedding, which is of minus 0.3, 0.7, 0.45, you'll multiply this with again WQ to get, sorry, not WQ, WK to get, let's say, 0.7, 0.8, 0.9. Similarly, you do it for value of SAT as well. You take the embeddings 0.6, sorry, what was it? 0.3, 0.7, 0.45. Okay. Multiply it with value. Right? Let's say you got this. You will do it, by the way, for all the words. Okay, all the focus words. Okay. So now what will we do to compute the dot products? So we'll need to compute the dot products, which will do it for, let's say, different words. For example, you will compute the dot product of sat with the other focus word. Let's say sat with cat, right? Then you will do it for other word as well. For example, let's say mat, sat with mat. Okay. So, for example, sat with cat, how will this happen? You will take the representation of your query, or so the formula is q dot kt, right? This will help you do the dot product. So over here, we'll do the same thing only. We'll take the query representation of sat, we'll multiply it with whichever word we are taking along with sat. We are taking cat over here. So we'll multiply with the key value of the cat. Only the key, no the value. So we'll multiply with key of cat, and we'll take a transform it for multiplication purposes. We need to take a transform. Okay. And this is how the dot product will be computed. Here we'll multiply q of sat with k of mat transpose, as we saw in the diagram as well. Okay. So once you multiply this, you will get your final attention scores, right? So you will get your scores based on the dot product, okay, of the self word of the word sat with all the other words. Okay. Finally, at the final layer, we'll apply the softmax function. So let's say you want to apply the softmax for your let's say sat and cat. So we'll compute the alpha. Alpha is softmax value between, let's say, you want to compute between sat and whatever word you want to compute. Let's say sat and cat. Okay, so what you'll do, you'll just use softmax on top of the score that you receive for sat and cat. Let's say this particular score you'll get over here. You'll pass the score in your softmax. Okay. So it will give you the final softmax value. Okay. Okay. So finally, for any single word, what will happen? The word will be, sorry, for any single sentence, you will get the different softmax value between different words, right? You will get like, let's say this is alpha 1. So you'll get alpha 1, alpha 2, alpha 3, alpha 4, and so on. Depends on the combination of words that you have, right? And this representation, when you represent all of these things, this is going to be a contextually aware representation. What does that mean? It means that it understands the context because it has taken into the account the similarity between words. Okay, it has tried to understand first of all on the focus words, and it has also tried to focus on those words which are similar to each other. Okay. All right. So in a way, this is the simplest architecture of transformer, but there are like many other advanced transformer that also exist, like multi-head and parallelization based transformers, which we don't have to cover. But even if you understand this logic until here, that is enough for your projects. Okay. All right. So feel free to customize your layers. Feel free to add the other things which you want to add. Okay. Talking about BERT, I just wanted to give you a small understanding of the very famous model, which is BERT. So we saw transformers. One specific example in transformer is the BERT. You might have heard of this. This is one of the top performing deep learning models. BERT stands for bidirectional encoder representation of representation from transformers. Bidirectional encoder representation from transformers. So as the name says, it's dependent on a transformer. It's a type of transformer only. Okay, and it I think got introduced by Google in the year 2018. Okay, very recent, not too old. Okay, so it was introduced to understand the ambiguous context, like words which or sentences where it's very difficult to understand the context. It's like highly ambiguous because you don't have proper positive, negative words or words which don't have any similarity. That's where they created BERT to handle those scenarios. It works really well to understand even the complex of words. Okay. Okay. So BERT is a pre-trained model. Okay, you don't have to train it; it's already trained. Okay, and you can just fine tune it based on your the data that you provide, like the question and answer data set, the data that you give. You can actually customize it according to your data set. Like you can make it adapt to your own data. Like just tell it what you're looking for. Just give it input, like just ask it question and also tell what is the answer that you're looking for. That's how you can customize it according to your use case. For example, let's say I want to train, or let's say I want to use BERT for my uh, pharmaceutical project. I will give some examples of that pharmaceutical project and I'll ensure that it understands those examples, and automatically BERT will get adapted using its architecture for my own data. Okay, that's how we customize it. So it outperforms BERT, outperforms a majority of many neural network architectures. Right? Whether you use token level, whether you use sentence level, whatever embeddings you use, but you'll see that BERT is highly powerful. Okay, BERT again has some like variations depending on the complexity which you are uh, trying to achieve based on the tokens. Okay, so we don't have to go into very deep of BERT architecture, but I'll just give you a small idea of how BERT works. So BERT represents the word. It represents a word using using the previous and next context. Right? So BERT will represent the word using the previous and the next context, and that's why it's highly powerful. Okay, and that's the reason why it's bidirectional as well. Okay, the B stands for bidirectional. What does this mean? So basically, this means that for a sentence, for example, let's say I accessed the bank, I access the bank account. I access the bank account. What does this mean? This simply means that you can use BERT to represent this in numerical form. Okay, so how can we do this? So it will create the embeddings based on bidirectional. Okay, based on bidirection, which means, for example, if you want to embed the word bank, okay, you want to embed the bank. So this embeddings, whatever embeddings it will create, that will take into account not only the like the words which are closer to it, but it will also take into the accounts the word before it, I access the, and it will also take into the account the words after it. Okay, so it will create an embedding using the words which are before it, using the words which are after it. Okay, and this generally doesn't happen, right? You don't create embeddings based on the other words which are present. Okay, and that's why over here it's bidirectional because it can go in both the directions to create embeddings for every single word. Okay. So you'll find BERT in a library called as Hugging Face. You might have heard of this library, which contains the BERT algorithm. So you can use Hugging Face to get the BERT. Right? It's one of the most complex model, and that's why we call it as state of art. Okay? Because it gives you very good performance as well. Okay, I think you all know about encoder and decoder, right? So BERT makes use of encoder and decoder as well. Okay, in like very simple form, encoder is what reads your input, right? Decoder is what produces the output. Like that's what happens. Produces the prediction or the output. Okay. But in case of, I mean, this is generally what encoder and decoder do in very simple terms. But in case of BERT, since we are using it, since it's a language model, right? Since it's a model which has specific application. We'll talk about the application. But over here, in case of BERT, we don't really need both encoder and decoder. Okay. Only thing that we need is encoder. We don't have to generate predictions. We just need to translate. We just need to give some specific output. Okay. So we'll talk about why don't we need predictions. We only need the encoder. Okay. Yeah. It doesn't require the decoder mechanism. Okay. The reason, because generally in any normal neural network model, which are directional models, right? All the neural network models are generally directional. They read the input from left to right? Sequentially from left to right, which is sequential. Right? But in case of BERT, it reads bidirectionally. It reads everything at once. Okay, that means it is reading from left and right, and it's reading everything. It's not that it's only reading from the left side. It's going in a sequential manner. No, it will read everything at once. Okay, and that's the reason why it's considered as bidirectional. Okay, so in a way, like a better word to call this would be like non-directional. Okay, because it's reading everything at once. So that's why we say it's not like left to right, but it's kind of bidirectional where you can say that everything will be read at once. Okay, but more specifically, it should be called as non-directional. But the name given to it's bidirectional. Okay, the main advantage, you understand the word based on the context, based on its surrounding, based on all of the surroundings. To be more specific, okay, which is a highly powerful thing to do. You can imagine like how difficult this would be. Okay. Uh, okay. Okay. Talking about the uses of BERT, so we know the reason why BERT outperforms is first, it only needs encoder. Second, it's bidirectional. And you can use BERT for a lot of things. Like it's already pre-trained, so obviously you don't have to worry about training it. So you can use it for a variety of tasks such as classification. Okay. All you need to change is just like add a small fine tuning, like add a small layer according to the final task. Okay. You can customize that much. You can already use the existing model, pre-trained models to just make some small changes. So you can do classification, you can do sentiment analysis. Okay. So all you need to do is just add a classification layer at the end. Then we can use it for question answering system, which is your chatbot. Right? So you can tell your chatbot that what kind of questions and answer does it want to learn. Like you pass some examples and it will pick up. Okay, this is the question and answers that you are trying to help me understand. It will understand the context. If you ask similar questions, it will be able to answer. Okay. We can also use BERT, by the way, for named entity recognition as well. Okay. NER. We have seen this previously. We know what is NER. So here you can use it to recognize the type of entities, for example, person, organization, date, and so on. All you need to do is just train, like using BERT, you can specifically train a NER model, model specifically meant for NER, which understands based on the sample data that you get, like what kind of output you are looking for. Again, it will understand how to identify the right context. Like, there are some limitations with BERT. You should know about them, right? Or let's say key takeaways. First thing, the size of BERT is very huge, right? It's very large. So there are total around 300 million, around 300 million parameters. which means it's one of the largest model of its kind, right? 300 million is a lot. You generally don't see this much parameters. Okay. Largest model of its. Okay. So obviously it's highly superior to other architectures. Okay. So if you have enough training data, then only things will make sense. But imagine if you don't have proper training data, like you don't have proper examples, then BERT will fail to perform because you don't have enough examples. So ensure that you have enough training data. Then only you can do you can get the best results. Okay, and it can improve your accuracy provided you run it for good number of iterations. Okay. The issue is the bidirectional approach which BERT uses. It converges, like finding the optimal loss value, finding the minima is very slow compared to the traditional approach of left to right. Directional or left to right approach. Okay, because obviously, like in left to right, you are going in a sequential manner. In the bidirectional approach, for every word, you need to take into account all the other words, right? So you can imagine how much complex that would be. Okay. But still, the performance will outperform the directional one. Okay. So this was like a very huge breakthrough in ML or NLP when it was introduced. And the reason, I mean, the feature that it has, like the flexibility to fine tune this and use it for a wide range of practical applications. Okay. It became one of the most advanced and powerful models. Okay. So now that we know that BERT can be used in chatbot, we'll focus on chatbot now. Okay. By the way, BERT is already used in all these tools like Google Docs, Gmail. Okay, where you're using all this thing. Let's say in Doc, it's telling you, do you want to generate text, right? Or let's say in Gmail, where it says what text would you want me to write. Right. Finally, going to the last topic. So we'll continue with this. NLP chatbot. So I think everyone knows what is a chatbot, right? You'd have seen it on websites, you would have seen it on WhatsApp, where you ask a question to the chatbot and the bot replies with an answer. Simple question answering system. It's nothing but a chatbot. Question answering system. QA system. Okay. Where you give some question and you'll get the answer. Okay, so in a way, we have all seen multiple types of chatbot. You would have seen chatbots in customer support, right? People like Zomato, Swiggy, they have a chatbot which tells about your status of order and some basic things. Even banks, when you call them, chatbots sometimes give you the answer. Okay, even credit card companies and all that. So this obviously helps people to reduce the manual effort, reduce the time for manual work, because you don't need manual labor for this kind of task. Even on WhatsApp business and all, right? You can set up a customer support. Okay, and by the way, right now there are like advanced chatbots which can give you answers in Hindi, in your native language. Okay. Okay. So coming to the types of chatbot, one is rule based. Okay. So rule based chatbot is like a old solution, very old. Like the most simplest thing that you can do is simply create a rule. For example, if someone asks me, let's say I'm organizing an event, if someone asks me what is the price of entry ticket, if someone asks me this kind of keywords where price, entry, and ticket are mentioned, like if I write a rule, like if you see price, if you see entry, if you see ticket, then give the output as 500 rupees. Okay, like this. This is a simple rule-based approach in which you have to manually define all the different kinds of question which you want the other person to answer. This is like very simple. You can write a Python program to create all this solution, right? You even a simple Python program with if and else can be act as a chatbot. You take input and you give some output, right? Very simple. Okay. But the challenge is this won't be able to handle a huge number of questions. Like this is fine. Like if you know that there are only 5 to 10 questions which the other person can answer, then I'll create a rule for those 5 to 10 questions and I'll keep it. But let's say if you are someone like Zomato or Swiggy who knows that there can be multiple types of questions, or let's say a big company who knows there can be multiple types of questions, then probably you need an advanced chatbot. Okay, so obviously it's not as powerful, but it's still simple for companies who don't have a lot of questions, who don't expect a lot of questions. Okay, so apart from this, you can use deep learning based chatbots. One simple thing that we just learned, you can use BERT to customize the chatbot according to your use case. Like you can tell BERT that what kind of output you're looking for by giving some data input, and it will understand the context. So if someone asks similar questions, it will be able to answer. Even though it's not exact match, but the words are similar, it will be able to do it. Okay. All right. So now you can use pre-trained advantage to train your custom BERT models, right? Custom chatbots. Mm, all right. We'll see examples of this just in a while. One last thing is LLMs, okay, large language models. So I think you're going to cover large language models separately. I guess you have a model for that. Okay. But just to give you a small gist, large language models, I think you would have heard about them very recently, right? For example, you might have heard of ChatGPT, which is again a very famous example. So large language models are a like recently, uh, you know, developed kind of models which are based on the logic of large language. We won't go into the logic of large language right now, but all you need to know right now is you can create LLM based chatbots. Okay, this is a different, you can just assume it's a different architecture. Okay, through which you can get you can again understand the context and it's highly powerful. Like you can imagine how powerful ChatGPT is. Okay, so this is LLMs are a topic which is based on generative AI. Okay, this itself is a very different topic. It's not the same topic as BERT. Okay, generative AI, we have not spoken about it yet. Okay. So generally in NLP models like BERT, you will be personalizing the content based on the examples that you give. LLMs may, it understands by itself. Like it has the potential to generate content on its own. Okay. You need examples, that's true, but it still has the capability to generate the outputs based on its own understanding, based on its own data. It will try to replicate the data that is given to it. Again, and that's why the name generative AI is coming. Okay, so we won't go into the specifics of Gen AI right now. You'll see this later. But let's see a code example for deep learning architectures. So let me show you a final code. Do you guys know PyTorch? Have you guys tried PyTorch?
No,
Okay, you guys have not studied PyTorch. Did you study TensorFlow then?
no.
So you have not studied TensorFlow. Then how were you creating deep learning models?
Yeah, deep learning model, they just theoretically explain, but we know that there is a package called TensorFlow, but
Oh, so
they have not
have
told
you
that in
guys?
detail. Yeah, only
That means
theoretical part they covered.
so that means you have not created a single deep learning project until now. Is that correct?
No, one project class recently it happened on deep learning, but I didn't attend that. But with others, you can confirm. Was
Okay,
that okay?
okay. I was of the assumption that you guys are comfortable with the TensorFlow or PyTorch, like either of one library, because without that we won't be able to build the deep learning models. Um, Cool. So, like, I will say everyone just recap on the project, whatever project was given to you on deep learning. That would be useful. I'll just try to give you a small summary of the NLP project over here. it's fine if you don't understand any single syntax, we can discuss about it. But let me just share you this.
In that recent project, I think he used Keras, I guess.
Oh, you use Keras only, right? Okay, that is fine. Keras is also.
Okay.
Okay, so let me share this screen. Okay, so I'll just share this link in the chat as well. So this is the official TensorFlow page where they have given this example. So over here, I know a lot of you might not have context regarding the code, but it's fine. I'll try to simplify this. So what is happening is you are going to perform sentiment analysis using now BERT model, okay, using your deep learning approach. Over here, so what data set is given to you? IMDb data set. We have already seen this is the movie review data set. We'll load the BERT model. Okay, this is loaded from TensorFlow, by the way. So remember, BERT is present across multiple libraries. Hugging Face is the official library from where BERT was created, but it's a pre-trained model. So what people have done is they have fine-tuned the BERT model and then packaged it from multiple other places as well. Like you'll find a lot of GitHub places where people have created variations of BERT. Okay, so over here we are taking one variation of BERT which is present in TensorFlow. Okay, but you can find one in Hugging Face as well. I can just show you Hugging Face BERT. Okay. This is the primary model. Okay, this is the official documentation for your BERT model, and you can go through this as well. Okay, so like they have some examples over here as well. If you are interested, you can check on the blog post as well. Okay, but this is coming from the Hugging Face level. Yeah, you can see like for different languages, how does it handle and all that. I just want to show one thing. Okay, so example, you see this simple transformer, right? This is another page like simpletransformers.ai. who have made use of BERT to create their own variation. Okay, and now they have created their own library, which is simple transformers. Okay, from where you can import your classification model. Okay, so this classification model is making use of BERT. Okay, do you see this BERT? And there's a variation called as distill BERT. Okay, which is what they are using. So people created their own library, own package. Like this person has created own package, simple transformer. You can go to the installation part, and you'll be able to install this particular library. Where is it? Python 5 because pip install simple transformers, right? So they have created their own package which is based on board. They have just maybe made some fine-tuned changes to the board and packed it as a library, and now they are create like you can create a model using the function using this calling this object classification model where you can pass board. Okay, but no, like the first one that started was Hugging Face. Okay, coming to this, so talking about BERT. So BERT, we already know that we can use it for a wide variety of applications. The name is bidirectional encoder representation from transformers. They are usually pre-trained, and they have been pre-trained on a huge amount of data because they are using around 300 millions of parameters. So you can install, this is one way to go about this. You can install TensorFlow library, which I guess you would have seen. Okay, this is the latest version, I guess 2.13. We can check it, but I assume it's the latest version. Okay, next, all this are related to your import packages. Simply, you will need to OS and util you can ignore if you are not handling the files. This is only for file handling purposes. But all these things are the ones which you'll need for your deep learning model. Okay. This Adam optimizer again is something which you would, in case if you want to use Adam optimizer, you'll use it. Else, it's not required. Have you studied about Adam optimizers? I think you would have studied this in deep learning as a theory, right? Adam optimizer.
Yes.
Yeah.
Okay. So this is something which is based upon your knowledge, whether you, how do you want to combine BERT with other layers, like with other optimizers, with other layers, right? We can customize that. And for this, we need to obviously import TensorFlow. TensorFlow Hub is where they will store the BERT model. So that's why we are importing TensorFlow Hub. And text, you will be using some package text, some examples to solve this problem. Again, that's why we are importing text. Like we'll use some features of text package, some pre-processing way, which is present only in text. Okay. Optimization is an optional thing. If you need an optimizer, then only import it. It's not needed. Matplotlib, you know, logger is just only for logging. It will just store all the errors. Wherever there's an error, it will keep logging them. Okay, so now you have a data set of 50,000 movie reviews. We have already seen this data set. You can download this data set from this link. So you can just get the file. This is a Keras package, which will help you get the link. You're just doing file handling just to ensure that you are able to download the file properly. Okay, so I won't go into the details of file handling. In short, it will just create this link from where you will be able to download the package. Okay. Okay, then you're defining some basic parameters. These are hyperparameters based on the neural network architecture that you are trying to create. I'll just talk about this architecture. So over here, you are going to create the BERT model from TensorFlow Hub. As I said, you need Hub where you'll have the BERT model. So there are variations of BERT model which we have not seen, but you can simply read about this. These are like, you can read about pros and cons. Over here, BERT based 7 more models. Like BERT based is the simplest model. Okay. So this was the originally trained model released by the original BERT authors. Again, others are like just small computations which others are made on top of it. Okay. So now you can select which model you want to use. Where's the code? Toggle code. Okay. So over here, you can get this name, like this is the small BERT package. So if you want to see the name, I'll just open this link, small BERT. So they are using this variation, which is small BERT. Small BERT. I guess it would be over here. Okay, do you see this? Albert is another variation of BERT, but it's a light version of BERT with a reduced number of parameters. As I told you, people have made some modifications to the BERT algorithm, and based on that, they have created like all these new algorithms. Okay, like Albert is the algorithm which is like a light version with lesser parameters. Okay, so here is where you can use this, but I wanted to see the small BERT example, but I guess it's not present over here. Then why is it redirecting to this link? Albert is there, BERT expert is there, Electra is there. Base will be there in the BERT model. Okay, I guess there is some issue with this link because small BERT is not present as a different library, or either it's present in some other library, which we'll have to check. Okay, maybe it's present in one of them. Anyways, the point that I was trying to make over here is, if you want to see the documentation, just open this hub. You'll find the pre-trained models over here. So is it mentioned over here? Can we find it? Let me see where this is coming in from. Okay, it's present over here. Yeah, this is the hyperparameters, and yes, here is BERT small. Okay. So basically, they are getting it from here, the BERT small model. Okay, so if you see in Hugging Face, they have created like the official page of Google. They have created like variations of the BERT model. So this model over here, they have specified like this is the variation with this hyperparameters, and you can see this hyperparameters over here. BERT small. Okay, you can see it is L4H512. Okay, this is nothing but your layers architecture. How many parameters are there in your hidden layer and the different other layers which you can check. So it's like a smaller model, and that's why the name small BERT has been given. Okay, so you can just pass on the link for this small BERT whenever you want to use it. So you can just copy this and just pass this to your model. Okay, this is fine. This is fine. This will be taken care by itself. Okay. You don't need to do that. Then you have herb.keras layer, which will help you in pre-processing the data. Okay. This is helping you pre-processing. Once it has been pre-processed, you pass an input. For example, this is such an amazing movie. You pre-process it and you will get the different outputs. Whatever outputs you need, you will be able to get it. Okay. So, okay, this is the main part which I want to focus here. Whenever you want to train a BERT model, we can use herb.keras layer. This will first, herb is the main part where you'll get the BERT model. Okay. So this is where you will initiate the BERT model. You'll create a BERT model of your own. And when you save this BERT model, okay, you can use it on your data. Like this is calling the BERT model as you, how you do it, right? You're saying like use the encoder architecture to call the BERT model, save it, and apply the BERT model on the text data. That's it. Okay, 2 lines and you will get the output because it's already pre-trained. Okay, and this is the output that you will be able to see. Like you can see the BERT model, the pulled output layers, the sequence layers. Okay, now as I said, people keep combining the BERT model in a complete neural network architecture of their own. For example, this person is trying to create this architecture where they're passing the input layer, then they'll have a pre-processing layer, then they'll apply a BERT, then they are passing a dropout layer, and then they're passing the classify layer, which is a dense layer, right? So over here, a person is creating their own custom architecture, and that's what they will be implementing over here. See, they're passing the input layer, then the pre-processing layer, Keras layer, pre-processing. Then they are passing this for getting the BERT model. Okay, you can see this is BERT encoder. And finally, you will have the classification layer, which is your nothing but dense layer. Okay, so you pass the dropout layer, and then you're passing the dense layer. That's it. Okay, so basically they are creating this same architecture which is given over here. Okay, and using BERT in between, they are completing their neural network. Like, so as I said, like you can combine BERT along with other layers, along with other architectures, depending on your use case, depending on what you want to do, whether you want to classify or whether you want to optimize in between. You can add an optimizer as well. Okay, and that's it. Like this, all things I think you already know since you know Keras. You are just calling the model that you created, build classifier model. You are just calling it, saving it classifier models, and then again applying it on the data. Text test is the name of your data set. You'll get the results, and you can see the sigmoid values. Okay, so this is the sigmoid value. Okay, I think binary cross entropy you would already know. So they are just optimizing it. They are using the Adam optimizer to optimize it. You can pass the written number of epochs. How many number of times do you want this to run and all that? You can pass the optimizer. So they are passing the Adam optimizer. Cool. So you can just apply the optimizer, the loss function. What metrics do you want to optimize it for? The training will happen for 5 epochs, 1, 2, 3, 4, 5, and you can see like what is the loss. So we are using binary cross entropy, and that's why you see the binary accuracy. This validation loss is nothing but the binary cross entropy loss. Okay, so seems like the loss has been not very well declining, I would say. At least the accuracy has been improving slightly. The loss, the cross entropy loss is, I mean, on your test data, it seems to perform well, but on validation loss, it seems to mess up. Okay, so that is one issue. But otherwise, accuracy looks good. So you can evaluate the model. The final loss is 0.45, accuracy is 0.85, still decent. You can plot the accuracy score and the validation loss. You can save your model, and the final output, like you are getting the sentiments. Okay, so here you're getting to see the score. I think the scores are representing where are the scores over here? Scores are nothing but the results. So results are what? Print my examples. Pass the results. Yeah, these are the sigmoid values. Okay, so basically it's giving you the probabilities with which you are going to classify as positive, right? Because I guess the class 1 is positive class. Okay, so this is such an amazing movie. The movie was great. The movie was meh, right? The movie was okay. The movie was terrible. In this case, like meh is where probably it should have given a lower score, but still it failed. But otherwise, for okay and terrible, it still gave, like very less scores. Like the probability is lesser, right? So it's classifying it into 0. But for this, at least the first two, it gave a higher probability. So it's still performing well, but not 100% well. Okay, but it's still fine. Okay. Cool. So this was like a very small summary of the code. I think the expectation in this lecture is you already know the coding of TensorFlow and BERT, and based on your deep learning lecture. Not BERT, but TensorFlow or PyTorch, either one. And simply thing that you need to know is how to apply the BERT. Okay, for which you just need to know which model name you want to pass. For the words small BERT, you can see other BERTs, whichever you want to see, you can find it in this Hugging Face only. Just go over here and you'll see the variations of BERT. Depending on your use case, you can pick anything. Like if I want recurrent gamma, I'll pick up recurrent gamma. I'll just copy paste this and replace the code over here with the recurrent gamma. Okay, and you can see like what it does. Okay, that's simple. Other things you don't really need. All these things you can ignore. These are like specific variations based on the developer. Then you can just pre-process it, and then you can just use the Keras hub, call the BERT model, apply it, combine with other layers if you want to do it. Again, it's a choice. And finally, you can just do the same retuning process of training and validation.
MJ,
Yeah.
can you please explain why you will use this Keras, PyTorch, and
So
without
Kera,
that, can't we do, or what are the
so
advantages? Or
yeah. So basically in industry, for doing any deep learning project, you have two options. Either will use TensorFlow or will use PyTorch. These are the predominant libraries that we have. Okay. Now, some companies use TensorFlow, some companies use PyTorch. The difference is not much. The kind of features that both of them offer is very same. Some prefer Keras because Keras is based on TensorFlow. It's offered by TensorFlow, and TensorFlow was created by Google, right? So some companies already have a environment which is based on, let's say, GCP, Google Cloud Platform, or they might have some partnerships with Google, and that's why they prefer using Keras only or TensorFlow only. Okay. Some companies like Amazon and all, they might prefer PyTorch, but the difference is hardly much. Like if I show you the difference, PyTorch versus Keras, so the main difference is with the documentation, with the support. Okay, but you can implement the neural network models based on both of them. Okay, so PyTorch. Okay, so TensorFlow, this is created specially by Google, which offers Keras. So you can compare all these things. Okay, coming to PyTorch. Okay.
not exactly the difference between those three, but
Mhm.
why we will use those? What is
So
why to use them?
So over here, as I said, you don't have specific application where you will probably say that I'll use PyTorch. Okay. The major decision depends on your partnership. Otherwise, there are like relative improvements. For example, PyTorch has limited, I wouldn't say limited, but comparatively lesser algorithms compared to TensorFlow. Okay, that's one thing. Second thing is, do you really need the left out algorithms? If you need it, then you will think about TensorFlow. But if you don't need all those left out algorithms, if you're fine with using all the common algorithms, then there's no difference in PyTorch and TensorFlow. Okay. The main decision depends on your environment. Okay. The Are you already settled with Google environment? Then you'll probably prefer TensorFlow. If you're not, if you're willing to explore a new platform, then it's your call whether you want to go with PyTorch or Keras. Depends on your call. If you tell me about documentation, I'll say go with TensorFlow because TensorFlow has much more better documentation compared to PyTorch. Okay, there are some little like advancements with both of them. For example, PyTorch is a little faster. Like as you can see, PyTorch has a higher speed. But again, this will hardly matter in your projects because we don't deal with very high amounts of data. This will be only visible when you are dealing with like TBs of data. Okay. Okay. So over here, Keras simplifies the journey into deep learning. This is mainly because the documentation is much more better compared to PyTorch. Okay, so like I think this architecture may be able to give you a more gist of it.
Okay.
One is with pricing as well, by the way. Keras is completely free, but I think in PyTorch there are, even though it's open source, there are some things which may be paid. I just need to verify this. Oh no, I think both of them are paid. Only thing is with Keras, when you use TensorFlow, you can use GPUs as well. So, for example, over here in TensorFlow, I have an option to use GPU. Okay, so we can make use of GPUs, which will make your processing. Even though GPUs may incur with a cost, but you can make your processing much more faster. Use a GPU. Okay. Okay. You can actually like try to read the code syntax. Some people feel that the coding of Keras is more useful. Some people feel the coding of PyTorch is more beginner friendly. But in my opinion, I always prefer TensorFlow because since I work with Google, TensorFlow is our recommended choice. Okay. Cool.
Okay.
Yeah. Okay, so you can see some examples over here if you are interested in looking at more examples. Some of them are based on image processing. So you can just go over here, you can search for bird and you'll get the list of articles with bird. Okay, so for example, this one we have seen, this is the chatbot question and answer. So I think they have created two chatbots, Android and iOS. Okay, so if you see this example, right? See, this is the chatbot which they created. You give a text query, when was TensorFlow released, and it will give an answer. Okay, you're creating this kind of chatbot using TensorFlow APIs. Again, I think they are making use of BERT. See, they are using a variation of BERT, which is mobile BERT, specifically designed for Android and iOS. You can take the Android example. You can check out the course. So this is the algorithm. They are used and they have developed the front end using the Android Studio, which will help you develop the front end now. We don't need to go into the front end part, but main thing that you need to know is they are using BERT in the backend. All right, guys, I think it's 9:45. Let's wrap up. So I know we could not have a smooth journey because of my own personal reasons, but hopefully the next time whenever we meet at a time when even I can actually, make this measure much more smoother and hopefully give you a much more better experience. But hopefully the time that we had together, you enjoyed learning, you found NLP lectures to be useful. Remember, NLP is very vast, so is your machine learning and so is your deep learning. That doesn't mean whatever we have seen as the end of it. There are many, many things which are still there. But given the time constraint that we are given a time constraint of 2 hours for a day of like 2 weeks. The best that we can go is still here. If you want to learn things on your own, feel free to just see more examples, see more projects. I can give you some ideas regarding from where you can continue learning. All the things that we have seen until now in 2 weeks is like 80 to 90% questions will come from there only. Okay, that's for sure. The rest 10% is something which you have to self explore. No other course will teach you from where these questions will come because it's highly unpredictable, right? Sometimes people may ask you questions from topics which you would have heard for the first time. For example, like when Jenny was coming up, I was asked question from LLMs, right? Where LLMs were not even like very popular. Okay, and courses at that point of time were not even teaching LLMs. So just note that this is not the 100% thing. This is like hardly 80 to 90%, but at least majority of your interviews on LP you will be able to tackle through this only. Okay, you can expect questions from modeling or your pre-processing. Mainly questions will be asked from both of them. Like if I show you some interview questions, you will be able to solve them. Like NLP interview questions, you would have seen most of them. Okay, what is NLP? What are the main challenges in NLP? What are the different tasks in NLP? All these are simple questions. This you already know. Common pre-processing techniques. We know the pre-processing techniques. This is all fine. Tokenization we know. NLTK library we know. Stemming we know. POS tagging we know. Name entity we know. Parsing is nothing but pre-processing. This is not like important. What are the different types? This is not required. No one is going to ask you parsing in nowadays. Vector space, you all know what is a vector. Bag of words, we know. Okay, so this is a variation like n-gram model. We already know. I told you about bag of words. You can create unigrams, bigrams, and trigrams or n-grams. So this is again something which we know. Term frequency, inverse document frequency, TF-IDF, we know. Cosine similarity, we have studied about this. Rule-based, statistical-based, neural-based. I think you should be able to answer this. What are the different ways you can create the models? Sequence, I told you what is the sequence. Like we have talked about sequence models, so you can read about this as well. Various type, I think this is quite easy. The different types of model. We have seen transformer recently. Sequence labeling, this is fine. Topic modeling, we know. We have studied about topic modeling. You should be able to answer this. LDA, we have studied. NDA, NF, we have not studied. You can study about NMF. GPT, we just smallly, like in very simple terms, discussed about GPT. But again, GPT is based on pre-trained transformer combined with generative AI. This you'll see in hopefully in, I think you have some upcoming lectures on Gen AI. So I think there you'll cover it. I'm not sure whether it's already covered or it's upcoming, but as far as I know, I think it's going to come up. Word embeddings we know. So you can answer all these questions, various algorithms, what to wake and all, CPOW and skipgram. We have seen this. Glove, we did not see. FastText, we did not see. Elmo, we did not see. So you can read this on your own. But we have already seen. Out of vocabulary words, as I told you, this is like a major challenge in which, if you remember in one of the starting lecture, I told you there are vocabulary words which may be out of context, and that is very difficult to handle. Okay, so for them, they are discussing some approaches which you can use. Okay, this is fine. This is some like challenges, word sense disambiguation. You can just read about this. All these are like basic things. NER we know, deep learning we know, hidden Markov model we have studied about this. CRF is again like not so much used nowadays, but you can still read about it. It's nothing but a variation of hidden Markov model. You can study about this. It's a specific type in which you modify the HMM. Okay, RNN I think you already know. Backpropagation you already know. Limitation of RNN you should know about this. LSTM you should know about this. GRU you should know about this. Sequence to sequence model. So this is nothing but encoder decoder. You also know about this. Attention mechanism, which we studied today. Self attention mechanism. Transformer we studied today. Self attention. Multi-head attention we have not studied it. You can read about this. This is again an advanced variation of transformer in which instead of using self attention you'll use multi-head attention. Okay, so you can read about this as well. Okay, positional encodings, architecture of the transformer, like you have an encoder, decoder, like this is general transformer, but in BERT, we don't need a decoder. Generative AI, machine translation, we have studied about this, like how you can convert, perform language translation. Here they're talking about this algorithms, but we know we can use BERT as well to do this. Blue score, we have not studied about this. These are some evaluation matrices, like these are some fancy evaluation metrics. Even if you don't use it, even if you use simple precision metrics like precision recall, accuracy, F1 score, I think those really perform well. In industry, unless and until you are working for an innovation team, we don't generally go into this evaluation metrics. We prefer our common standard metrics only. Okay, so these are the common evaluation metrics. As I said, like we generally focus on that only. Hardly you'll see like we use it because see, text classification, you'll use the common ones. POS tagging, NER, you're using the classifier. Passing, skilly, you can go with this, but passing hardly we have application of passing, and even co-reference resolution we don't really need it. Okay, so you can check this chatbot F1 score and all that. This is fine. Okay, that's it. So as you saw, like major things we have already covered. There are a few like little nitty-gritties which probably you'll have to study on your own, because all those are variations and there can be hundreds of variations of every single model, and it's not practically possible to cover everything. Good. I tried my best to give you a small flavor of whatever is required. Hopefully you enjoyed the lectures, and that wraps up our NLP lectures. In the future, hopefully we get some more lectures in which we can study together, and yeah, let's continue learning together. Okay. Any questions, people? Okay. So keep learning, keep exploring, keep building your projects. If you want, I can just give you one link for building a project. So just take this link. You have not studied ML ops, right, until now? Okay. See if you can learn ML ops from this. Okay. Just go through this link and you will be able to understand the complete architecture. Okay. Here it contains BERT as well, and it contains traditional ML models as well. Okay. So this is a Medium article which is creating an end-to-end model. Okay. A simple model. It's not very complex. You should be able to understand it. And finally, you'll be able to create an app as well. It's creating like an interface through Gradio. Gradio is a library which helps you to create a small app like an interface. Okay. Cool. I think that's pretty much for today. Let's wrap up. I'll see you in the, hopefully we meet in the next lecture. Thank you. Bye and have a good day.